Imagine you're on the bridge of a ship. It's the middle of the night, and a thick wall of fog just rolled in. You can't see a thing.
Nothing.
And you know there's another vessel out there, maybe just a mile away. How do you find it? How do you avoid it?
That is the exact scenario that makes marine radar probably the most important tool on that bridge. And that's what we're going to get into today.
Exactly. This is a huge topic for safe navigation. Our mission for this deep dive is to use some really great technical material to understand how radar works.
Right.
What are the different types? And what you told me is the single most important lesson.
Right.
Why you can trust its distance measurements way more than its direction measurements.
Yes, that's the core takeaway. It's essential for anyone learning about seafaring, especially cadets who are just building that technical vocabulary.
So we're going to keep it simple and practical.
Absolutely. We'll simplify the science and just focus on what you really need to know for safe operations out on the water.
Okay, so let's start with the basics. The word radar, we use it all the time, but it's actually an acronym, isn't it?
It is, and it tells you exactly what it does. It stands for radio detection and ranging.
Radio detection and ranging.
At its core, it's just an electronic system that uses invisible radio waves, microwaves specifically, to, well, detect objects and figure out how far away they are.
And it really becomes the ship's main set of eyes when visibility is bad.
Oh, absolutely indispensable. When you have fog, heavy rain, or just total darkness, the radar is what you rely on.
So what are its primary jobs? I think most people would say collision avoidance.
That's number one for sure. The international rules, the call regs, they legally require you to use radar to spot other ships and hazards.
To prevent accidents.
To prevent accidents. But it's not just about avoiding things.
What else?
Well, the second major function is just pure navigation. You can use it to find your ship's position, what we call a fix, by measuring the distance and direction to things you know are fixed, like a lighthouse or a specific point on a coastline, or even a buoy.
Okay, so it helps you avoid other ships and it helps you know where you are.
And third, it gives you situational awareness. It gives you a constant bird's eye view of everything happening around your ship.
You can see traffic patterns, see dangers miles away, things you could never see with your own eyes.
Exactly. And the fourth role, which is really important, is weather monitoring.
Because it can see rain.
It reflects very strongly off heavy rain. So you can see a big storm or a squall line coming and steer away from it before you're right in the middle of the worst of it.
Fantastic. So we know why we use it. Let's get into the how. How does it actually work?
Okay, so it's all based on the principle of reflection. We can break it down into about 5 simple steps.
Let's do it.
It all starts inside a box called the transmitter. This thing sends out incredibly short, very powerful pulses of electromagnetic energy.
And these pulses don't just go out in all directions. They're focused by that rotating antenna on top of the mast, the scanner.
Precisely. The scanner takes that energy and shapes it into a very narrow focused beam. Think of it like a searchlight.
And it's constantly spinning, sweeping 360 degrees.
Right, so that pulse travels out, hits an object, another ship, a coastline.
A rain cloud.
A rain cloud, yeah. And a tiny, tiny fraction of that energy bounces off and comes back toward the ship. That's the echo.
So the antenna that just sent the pulse now has to listen for that echo.
Yes, it immediately switches to being a receiver. It catches that extremely weak signal that comes back.
And that's what creates the blip on the screen, the display that shows you the range and the bearing.
Exactly. And let's start with range the distance, because that calculation is just so reliable.
This part is amazing. It's called a time of flight method, and it all comes down to one constant.
The speed of light. We know that radio waves travel at a constant speed, about 300,000 kilometers per second.
And the radar has a super precise clock inside it.
An ultimate stopwatch. It measures the tiny, tiny time delay between the pulse leaving and the echo returning.
We're talking microseconds here, right? Millionths of a second.
Yes. And the math is actually simple.
Yeah.
Distance equals the speed of light times that time delay.
Divided by 2. Why divided by 2?
Because the pulse had to make a round trip. It went out to the target and back again. So we only want half of that travel time for the distance.
That makes perfect sense.
And it's incredibly precise. If a round trip takes just 1 microsecond, the target is about 150 meters away. It's because that speed is constant and the timing is so accurate that we trust the range measurement completely.
Okay, that's distance. Now what about the direction, the bearing?
Well, this is all about where the antenna was pointing. Remember that narrow focus beam?
Yeah, the searchlight.
As the antenna rotates, a device called an azimuth encoder tracks its exact angle at every single moment.
So when the echo comes back, The system knows, okay, the echo arrived at this exact microsecond, and at that instant, the antenna was pointing at 0 force 5 degrees.
That's a perfect summary. That combination of time and angle tells the display exactly where to put the blip on the screen.
But you mentioned this is where we start running into some problems, some limitations.
Yes, and those limitations are exactly why large ships don't have just one radar. They usually have two different types.
Right, different tools for different jobs. These are the X-band and S-band radars.
Exactly. They operate on different frequencies, which means their radio waves have different lengths, different wavelengths, and that changes everything.
Okay, let's start with X-band. That's a higher frequency, right? About 9 gigahertz.
It is, which means it has a short wavelength, only about 3 centimeters.
And what does that do?
That short wavelength is its superpower. It allows the antenna to create an extremely narrow beam, and that gives you very high resolution.
So it paints a really sharp, detailed picture.
Crystal clear. If you're navigating a narrow channel or trying to dock, the X-band is what you want. It can tell the difference between two small buoys that are very close together.
It's for close-up, detailed work.
Absolutely. Pilotage, coastal navigation, that's its strength.
But there has to be a downside.
There is. Those short waves get easily blocked or scattered by small things, like raindrops, or sea spray, what we call sea clutter.
So in a heavy rainstorm, the screen can just get washed out.
It can get saturated. Yeah, it can essentially blind the radar to smaller targets that are hidden in the rain.
And that's why you need the other one, the S-band.
That's why you need the S-band. It's a lower frequency, around 3 gigahertz, so it has a much longer wavelength, about 10 centimeters.
And those longer waves can push through the rain better.
Much better. They are far less affected by rain and spray. The signal penetrates bad weather more effectively. The S-band is the workhorse for open sea navigation and for when conditions get bad.
So a professional navigator is probably running both at the same time.
That's the standard, yes.
Yeah.
You use the X-band for that high-res picture close by in clear weather, and you trust the S-band for long-range detection and to see through a storm.
Now, it's worth saying these systems don't work alone anymore, do they? They're all connected to GPS and computers.
That's right. They feed their data into systems like ARPA automatic radar plotting aids or target tracking.
And these tools?
Yeah.
They do the calculations for you.
Yeah, they do. They automatically track other ships and calculate things like their course, speed, and most importantly, if you're on a collision course.
That sounds like it solves all the problems, but this brings us to the main lesson of our deep dive.
It does. This is the crucial insight. Even with all those computers, you, the navigator, have to know that range is fundamentally more accurate than bearing.
Let's really break down why. The accuracy of range goes back to what we said earlier.
It's all about that precise timing. The measurement relies on the constant speed of light. The timing errors are so small, so minimal, that the distance calculation is accurate to within just a few meters.
And there are official standards for this, right? The IMO.
Yes, the International Maritime Organization requires range accuracy to be within 30 meters or 1% of the range scale. It's incredibly precise.
Okay, so that's range, rock solid. Why is bearing the direction so much less reliable?
The main problem is something called beam width distortion.
Right, you said the beam was narrow, but it's not a perfect laser line. It has a width.
That's the key. It's still 1 to 2.5 degrees wide. So when that beam sweeps across a target, the echo comes back from the entire width of the target.
Not just the center.
Not just the center. The radar can't tell you exactly where the center is. It only knows the target is somewhere inside that 2-degree arc.
So it kind of smears the target on the screen, makes it look bigger than it is.
Exactly. And it introduces an error.
Yeah.
And that small angular error becomes a massive distance error the farther away the target is.
What kind of error are we talking about?
Well, the sources give a really dramatic example. A 1-degree error in bearing for a target that's 12 nautical miles away results in a position error of over 1,200 feet.
1,200 feet. Wow, that's the length of 4 football fields.
That's a huge difference. It's the difference between a safe pass and a collision, all from just 1 degree of error.
And that doesn't even count other little errors like the ship's gyro not being perfectly aligned.
Correct. It all adds up. So bearing is good for getting a general idea, but you never trust it for precision.
So what's the practical takeaway for the person on the bridge? If ARPA is doing the math, why do they need to know this?
Because the ARPA is only as good as the data it gets. If the bearing data going into the computer is flawed, especially at long range, then its collision warning might be unreliable.
The computer can't fix the physics of the antenna beam.
It can't. So the human has to know this. When you are fixing your own ship's position, you use 3 or more radar ranges from lighthouses or coastlines. You don't use the bearings.
You use the reliable measurement.
Always. And for collision avoidance, the golden rule is constant bearing, decreasing range.
And that rule works because you are trusting the change in range, that super reliable distance measurement, as the true sign of danger.
That's it. You trust the timing above all else.
This has been incredibly clear.
Yeah.
So to sum it all up, radar works by timing an echo that moves at the speed of light.
Right.
Big ships need 2 types: X-band for a clear, close-up picture, and S-band to see through bad weather.
The high-def camera and the workhorse.
And the most critical lesson: distance is more reliable than direction, because timing the speed of light is just more precise than measuring an angle with a wide beam.
And that leads me to a final thought for you to take away. We've said that range is perfect because the speed of light is constant. But that radio wave is traveling through the atmosphere.
Okay.
So, here's something to think about. Could anything in the atmosphere, like big changes in temperature or humidity or air pressure, could anything like that actually bend the path of the radio wave or slow it down, even just a tiny bit?
I never thought about that.
It's an effect called atmospheric refraction. It's usually very, very small. But understanding that it exists is the next level. It's the difference between knowing the rules and truly mastering the science.
A great question to keep you thinking and digging deeper. Thank you for joining us for this deep dive into marine radar.